on the physics and astrophysics of gamma ray bursts, and the second on multi-messenger aspects. So Elisabetta Bissaldi is from INFN and Politecnico di Bari. She's a member of the Fermi collaboration, Fermi-LAT collaboration, also a member of CTA, so a well-known expert of gamma ray bursts, and it's a pleasure to have you here, Elisabetta.
Thank you. Please,
you can start. Thank you very much.
Thank you, Ulysses, for the invitation to be a lecturer at this school. I'm very happy. It's my first time in Sao Paulo. And last week was my first time in South America in general, and I was attending the conference, the HIPRO conference in Rio. So a lot of first times. Okay, so today I will give these two lectures. They are pretty dense. In the sense that I have, so usually my talks, I have very few written text and just figures and plots and images, while for these kind of lectures I prefer to have a little bit more text, because I assume then we will share the slides with you guys so that you can have some text and some slides for your convenience also after the lecture is over. I will focus this first part on gamma ray bursts. I always like to have, let's say, a historical view of gamma ray bursts, in general of the topics that I have to talk about. And so then I will focus a little bit on the Fermi observations, because as Ulysses said, I am a member of Fermi, both collaborations, GBM and LAT, and then I am also a CTIO member and also an affiliate member of the HES collaboration, so lots of collaborations. Okay, I don't know how many of you know a little bit, nothing, something, about a little bit. Okay, this is good. About gamma ray burst, we will start really from basics. I like this slide very much because it's, well, this slide is actually this animated GIF, because this is something from the 90s, I think, and I didn't find any other GIF like this, because this was used when I was a student to explain how bright a gamma ray burst is, and on the left you have the high energy sky seen by IGRET, by the IGRET telescope, and then on the right you have the light curve, so the cumulative counts that the instrument is measuring, and in the moment you have the gamma ray burst, the counts are going up, and you see a burst of gamma rays that is so bright that this is somehow flashing out the whole high energy gamma ray sky. It's a bit exaggerated maybe, but it gives you the idea. So these are the, let's say, most energetic explosions that we know can happen in our universe, and I like this view very much. But they are not only super bright in, let's say, in gamma rays. Now we know that they can also emit in the whole electromagnetic spectrum, and this we will see during the talk. And so this is an example of 2008, the so-called naked eye GRB, because the emission from this GRB is here in the center, and it was so bright that it could be seen also, let's say, with the naked eye. So it obviously in the optical, we will see what kind of emission this is, and this is one of the most, let's say, famous cases that was in brightest cases. I have, as I said, I have a few more informations. I will maybe not comment them all today, otherwise it will be too long, this talk. Okay, this is a little bit the, let's say, the outline of my talk, which is basically what happened over the past 70 years with gamma ray burst studies. So we will start from the so-called dark era, so from the 70s when they were first discovered. Then we will go through the Batse era, the Beppo-Sachs era, in which we learned first spectral and temporal properties, and then finally we understood something more about these other emissions, so this afterglow, this emission which is not only in gamma rays, but also in the X-rays, in the optical, in the radio, and all of this. Then there is a little bit of this HET2 in which we see there is the connection with supernovae, but I will go pretty fast about this. And then we start with these, let's say, these last three, which are still ongoing, because basically I am basing all of these from observations to what we learn about it. So basically, these are all missions that studied gamma ray burst. We have Swift, Fermi, and then all of the very high energy instruments that Professor Aronian already discussed, and you will listen a lot more over this week. So what did we learn with Swift about the afterglows, with Fermi about high energy, that I will focus a little bit more, and with the Cherenkov telescope with very high energy. In fact, I like to, so this is an adaptation of a slide by Lorenzo Amati that was adapted by another very good friend of mine and colleague, Professor Longo, and I readapted it. So this is the third readaptation of this slide, basically. And I would like to also to push inside these eras also the multi-messenger era, and this is also what we will see this afternoon, because we will talk about gravitational waves and the connection with gamma ray bursts, so this we will see it later on. Okay, the dark era, Felix already briefly mentioned about what happened in the 70s with all of the, well, actually what happened in the 60s, let's say, in which you had all of these satellites that basically were military to see what was happening, because, you know, there was this nuclear ban treaty about the different nations, basically the US watching over Russia in order to be sure that there were no nuclear bombs exploding around the Earth or on the moon or something like this. And so, because of this, there was this series of satellites which were called the Watchmen, these Vela satellites, that were monitoring, basically, with some instruments that could detect, obviously, what is produced by a nuclear explosion. And so, what was happening is that one of these, well, in fact, then most of these satellites, but in particular in 65, this Vela 4 detected the flash of mysterious gamma rays. And so it was not able, these kind of detectors were not yet able to understand the origin, obviously, from what direction. Only at the end of the 60s, there were these Vela 5A, 6A, they had consecutive numbers, were able to have the timing accuracy to reconstruct a little bit the source direction, and it was, in fact, excluding the Earth, the Moon, and the Sun. Because at the beginning, we were thinking, okay, maybe it's some nuclear explosion from the atmosphere or from the Moon, but they understood that it was not coming either from these three sources. So, so obviously, it takes some time to, since this was a military project, to get access to the data, to analyze the data, and to do something scientific with the data. So this is just the light curve of the first published gamma ray burst. It was published then in 73. And this is 670702. So the numbering scheme of gamma ray burst, maybe some of you know, it's first the year, then the month, and then the day. So this happened in 67, in July, the 2nd of July of 1967. And this is the first light curve of a gamma ray burst in which we have. So what is a light curve? You probably all know. You have seconds, so the time series on the x-axis, and then you have the count rate of your detector on the y-axis. And what you can already see is that it's not something, let's say, just you have one spike, and that's it. You have one spike, then a valley, then again a rebrightening, then it's going down. And the level which we assume, so it's the so-called background level in which basically your instrument is, let's say, it's always counting something, actually. This is normalized because usually your detector in space is constantly detecting something, but in general, so you have some counts over background, and it's pretty intense. So you have these two defined peaks. The other thing that I want you to look at is how long this is. So it's a pretty short signal. So because we have, in 5 seconds, more or less, everything is gone. And the problem is that this was not repeating. So you had one of these bursts, and that's it. And then, okay, also when you could have also some directionality, I mean, so from the same direction, you did not have twice or 3 times. You had just one from one direction. And that's it. So as I said, it took many years, from the 60 to 73 for Klebsadel to finally publish a scientific paper about this. The first paper had 16 events that were seen by the Vela satellites in this time range. What was the energy range of this mission? So between more or less 200 keV and 1.5 MeV. So let's keep this in mind because we will see then what all the other satellites and experiments have. But so it was really in the good range for gamma ray burst science. This is spoiler alert. Okay, so the time range we had something from even less than 1 second, so extremely fast source signals, to let's say 30 seconds, to just 16 events. So I mean, there was not so this big population. Some had no structures, others have lots of peaks and other things. We did not have any spectra with this type of missions. So, okay, moving on, in other times, so there were more with gamma ray burst, and also by other satellites were confirmed all of these events for 20 years. So now we are just basically skipping in one slide from 73 to the 90s, because nothing more happened in all of these years, because basically there was no dedicated mission about this. There were, as Felix said, there were missions dedicated more to the galactic plane, to the galactic center, to galactic sources rather than gamma ray bursts. So basically for 20 years they remained like not well known. There were a few hundreds of events, of flashes, but they were just roughly localized. They did not repeat, so if you catch one and that's it, they vanished too soon, and they were leaving no traces in gamma rays. Nothing. Okay. So interpretation. There was one of these, there are still these, Texas Symposium is a very famous series of symposia, and in 75 there was one on relativistic astrophysics, these Texas Symposiums, and in this conference there were like 100 papers, well, 100 contributions submitted to these conferences, proposing theoreticians, exactly. So they had about 100 models of what could gamma ray bursts be. And let's say most of those papers believed gamma ray bursts were galactic, somehow connected to compact objects, binary stars, something nearby, since they were so strong, so powerful, so something happening in the galactic plane, well, the galactic plane, the galactic disk in our galaxy, because basically on the absorption features, also the high energy emission features. So basically this was the main idea. But as I said, all of the experiments in the 80s didn't have, they were not sufficiently conclusive, and there were no counterparts. So it was just these bursts in the gamma rays that alone were very difficult to make any interpretation. And this is why they were, as I wrote here, so they acquired some special aura. So somehow they were these mysterious objects, and I have to admit, so I started studying astrophysics at the beginning of the 2000s, and also in those years they still had this mysterious aura, even after, let's say, 40 years of studies. The problem is, so this is something that is still true today, so there are no two identical GRBs. So once you have seen one GRB, you have seen one GRB. Basically, then now we also, after so many years, we have some good statistics, we see some similarities, but in general, there are no two identical events. The duration, the number of peaks, the brightness, everything can be different, in principle. Okay, so let's move on to the 90s. In the 90s, it was this wonderful mission that was one of these great NASA observatories, like Hubble, which is still up there. The Compton Gamma Ray Observatory is not up there anymore. Unfortunately, it was decommissioned in 2001, and it was launched with a space shuttle. It's amazing. And in the second picture, you see that the space shuttle is open and it delivers the instrument in space with astronauts. So it was delivered, also like Hubble and the others, so they were delivering the instrument. And the third plot is the instrument itself. Well, actually, it carries more instruments. So there were 4 scientific instruments, which I believe I have another slide about. Yes. Okay, so let's see if this is working. Yes. So basically, you have, it was huge. This was really big. The instrument, you have the spacecraft, and you have these 4 scientific instruments that you have in this table here. So we are not interested in all of them, but I just want to mention a couple of them. So this guy here, the Burst and Transient Space Experiment, BATSE, was the experiment. So it was built for studying gamma ray bursts. And basically, it was made of all of these detectors. There were 8 of them around the spacecraft. You see here, here, on the back, and on the side. So it was monitoring the sky from all directions, and it has wonderful spectral and temporal capabilities. So it was really the instrument. And then you had other instruments on board, obviously, like COMPTEL. And COMPTEL is also very famous because basically, I don't know if some of you are working in the MEV energy range, but this is really where we are missing the most information, because after COMPTEL, really there has been no true successor of this kind of experiment. So we are still based on what we learned in the 90s with COMPTEL. And then IGRET, which we will discuss a little bit more, because it was the predecessor of Fermi. Similar, so to say, in a different version, but the energies were, let's say, high energies. So there was also some possibility of studies of gamma ray bursts with IGRET. So the energy range of BATSE was from the low keV, so like from 30 keV, going up, let's say, to 2 MeV. Okay, so again, it's like in the villa. Actually, it's going a little bit more lower in energy. So to 30 keV, it's definitely lower. So regarding to the definitions that we heard before with Felix, you might even argue, oh, maybe it's more towards the X-rays. But OK, let's say for me, gamma rays start at 10 keV. But this is really, it really depends on who you're asking. So for some people, it's starting only at 100 keV or at 1 MeV. For me, it's OK from 10 keV up. OK, so these instruments were the instruments, basically BATSE. This was the success, the most, I think, the most important first success of the BATSE instrument. So what we are looking at here is a sky map. So it's the sky in galactic coordinates. And so do you see some, let's say, pattern? I don't see any pattern. It's just a lot of points on the sky map. What does it tell us? There is not the galactic plane. So otherwise, if it would have been galactic sources, we would have just seen the galactic plane popping up, and the rest would be, let's say, empty. Instead, we have a colorful sky map in which the gamma ray bursts detected by BATSE are basically homogeneously distributed over the whole sky, and this means they have to be somehow cosmological, so coming much more far away from us than what we expected. So beware, so this was still before we could have any other counterpart information, so this was already an extremely strong argument only based on gamma ray information. Okay, so these were, so these were basically all of, it was a map now at the end of the mission, obviously, because these are all the events seen by BATSE in the last catalog, the 4B, the last catalog that was published after the decommissioning of the instrument. And so basically, it's the biggest sample that we had prior to Fermi to learn everything we know about gamma ray bursts in the gamma ray energy range. So some milestones, these I already said, angular distribution. They are isotropical distributed. So basically, this is strongly suggesting a cosmological distribution. Temporal properties, so how long are gamma ray bursts? This is the historical histogram of the 90s made by Chris Akoveliotou and collaborators. what do you see? So here is the distribution in seconds. And you see we have a bump here below and another bump at longer duration. So basically this means we have a lot of events, but basically they are clustering somehow into different duration. What could be hinting to? This could be that there could be two classes, maybe somehow there could be two different origins of the two, or two different mechanisms or something. So some are extremely short, and some can also tend to be really long. This is only gamma, because this is in the 50 to 300 keV energy range. So we are not talking about other wavelengths. It's purely the gamma duration, okay? So what happened at the time that we introduced, it was introduced a definition of the duration which is called T90, which is the time between the 90% of the flux of the source is measured by your instrument in this energy range, 50 to 300. There is also the T50 distribution, which is the 50% of the flux, okay, but we are not that interested. So remember the T90. So T90 gives us an idea of how long the event is, and traditionally, and this is when it happened, because still nowadays we use this, let's say, division, we describe the long burst as longer than 2 seconds and the short burst as shorter than 2 seconds. I will show you that this now is a little bit an old style definition, and I don't like it very much. So there was a lot of discussion in the 90s, is there a third class? There was a lot of discussion also nowadays in the last 15 years with Fermi data. I will show you some update of this plot. Yes? Cosmological, it means it's far away, so it's not local. In the sense, it's not in our galaxy, but when you talk about the cosmological distribution, it means extragalactic. Easier term. Okay, and as you see, there seem to be more long than short GRBs. So this, again, is to be discussed. Can this be an instrumental bias, or is it really true? Okay, also this we can rediscuss later on, but in general, we detect more long than short GRBs, so 70 to 30% roughly, let's say. Light curves are very regular. These are just a collection of four events in the 90s. But you see, so all of these are gamma ray bursts. They don't look alike in any possible way because they are completely spiky. They have some quiescent periods, or they just have, boom, a super spike, and then they go down, they decay slowly, they so-called fast rise and exponential decay, like the one on this. Or they just go up, remain up, and then go. There are, as I said, there are no two identical GRBs. They can have quiescent periods, I already said. They can be very variable, so this, basically I already said it, but if you go and study how long these pulses are, because this was just, let's say, a collection of how many spikes you have, but you can go deeper in the matter and do all of the possible studies about how wide, how large are these pulses, so you can study the duration of the single pulses and see how they can vary in a very large range, also down to the millisecond scale. They can really go down to very fine scales. And this is an argument that we will see then later on, because this argument of the flux of the source that is varying so dramatically on this so short time scale is what is linking the event to how big the emission region is. So the shorter time scale, so the more compact the emission region can be. They are also asymmetric, as I said. Okay, you can have, not all peaks are the same, though, so they can have these maybe incredible fast rise and then these long profiles, decaying profiles, or they can have other shapes. So there are really various, there have been decades of studies about all of this. Let's focus for a moment on spectral properties, because this is one of the most important parts of gamma ray bursts. So how do we fit the spectra? Okay, so basically the GRB spectrum is the so-called non-thermal spectrum. So you don't use, if I can make an example, you don't use a black body, okay? You have something else, and it's basically non-thermal, and basically your full emission is in that energy range, okay? So we are, let's say, from hundreds to keV up to the MeV. So in this representation, actually you actually have two representations. So on top you have basically the flux in photons per centimeter square, per second, per energy, in this case per MeV. And you see here the photon energy. This is an example of a GRB of the 90s. And you see you have this spectrum that is somehow curved, let's say. Maybe a better representation that maybe some of you are already a little bit familiar is the spectral energy distribution, the SED, so to say. What we call it in the GRB world is more the nu-f-nu spectrum. So you multiply the spectrum by a squared, basically. It's like the SED. And in this representation, it's the same. It's the same idea. It's just two different representations. You have more than, instead of what we call a break in the power law, in the broken power law, we have like a peak joining the power laws. So the scientist who dedicated, let's say, the most, basically his life in studying this spectral distribution was David Bend in the 90s. And this is why, let's say, the spectral model that we use still today to fit gamma ray bursts is called the Bend model in honor of him. And basically it's two smoothly joining power laws, and I will show you a little bit more details here. Okay, I put everything. I don't want you, let's say, to learn now the function, just to give you all the details. So this is the low energy distribution that is valid from the break energy below. So this is the low energy part, and the important parameters are, okay, the break energy, obviously, the alpha parameter, which is this one, which is basically giving you the power law index, the low energy power law index. And then we have the high energy index, which is this part of the distribution, which is called beta. And in this representation, we call the energy the so-called E peak, while in the upper representation, we call it E break, and the two are, let's say, connected by this expression in terms of alpha and beta. So this is the function at low energies, and this is the function at high energies, a little bit different. And you have that beta is usually smaller than alpha. So this is more shallow, and this is steeper when you go down to higher energies. And we will see it also with more, let's say, this is something that we saw with BATSI, we learned with the BATSI data, but we will see obviously also with Swift and with Fermi, it's the same. So just, so okay, this I already saw. So let me just point to this fact. So basically, the idea of the band function was somehow an empirical description. So it is called, most of the time, a phenomenological model, okay, to try to best describe your data, to best fit your data. So there is not a direct physical motivation. However, this is just, so to say, a small, okay, I put it here. Okay, here I have just the same. I can skip this because basically okay, this is the same. I just wanted to go here. So over the past 40 years, there was a lot of studies, obviously. So this is a little bit of a spoiler to what we know today about spectra of gamma ray burst. And basically, the idea is that it is a synchrotron spectrum. We heard Felix this morning talking about this. And however, it is a little bit more shallow than a synchrotron, a pure synchrotron model. So this is a little bit what is making the theoreticians go crazy, because it's true. Because basically, in the synchrotron model, you have different characteristic frequencies in which you expect to have a certain certain decays of your power laws, and not all GRBs can be described. So in fact, very few of them. So it's a little bit complicated to understand. But I wanted just to point out that there has been really a lot of studies over the past year, and so if you are interested, if you're curious about it, I want to suggest you these readings by Ravasio and by Oganesian that are really, so there are also a few more recent ones, but these are the best ones, in which they try to model the synchrotron, and the part in which they succeed the best is actually this part here, but you see the energies. So we are moving, so to say, a little bit far away from the high energies that I want to talk to you about today, because this is better in the lowest energies, where unfortunately, so these are, for example, these are Fermi data. And Fermi data get worse because GBM in the lower energies is not such a good instrument. And so there are not so many events that are bright enough to have very good statistics in this part here. But as I said, so if you are curious, I really advise you to take a look at these. There are some reviews, very interesting ones, that tell you a little bit more about this. Okay, so these spectral parameters that we have to remember so are alpha, beta, and the peak. And these are some of the distributions that came out of, let's say, the whole analysis of the GRBs by Bazzi. You see, just to give you an idea, so alpha tends to be clustered around -1, beta around -2.2, 2.3, and the E-peak is, let's say, peaked around 220 kV. But you already see, I mean, it's pretty broad. You see how broad even E-peak. So it's really difficult to join these observations with theoretical models, because, for example, for theoretical models, there are lines that you can draw over this distribution that are the so-called, they call it the line of death, in the sense that theoretically the synchrotron model would completely tell you that it's not even possible to have this kind of value, while you have all of these distributions that have, let's say, non-standard fits. So this makes theoreticians still crazy today. I think I will skip the hard to soft evolution. What time is it? 36. And also the hardness. So maybe this I can just tell you a word about. So basically, I told you about long and short bursts. So one of the first things that was noticed in the 90s was that short gamma ray bursts tend to have some higher energy. So they are called harder in the sense that the spectrum is a little bit harder, while the long ones tend to be softer. So this is a particular representation of this so-called hardness ratio, in which you take the counts of the bursts in one energy range, you divide the hardest energy range, you divide it by the soft one. Okay, it's all complicated, but basically you see that there is a clustering also in this representation when you put inside also the spectral information, and you see that the long events tend to be a little lower. In the Fermi GBM you can see it better than in the Bazzi data, but anyway, and in the short ones they tend to have some, they tend to be a little bit harder, and this we also saw it with Fermi. High energies. Okay, I told you. Yes, sure.
So you say, for example, the long time is more or less low energy.
Well,
You have like a component which is high energy and shorter inside the. No.
This is a very good question. Indeed. Another thing that I'm not talking about today because it would be too long is that obviously these are the so-called time-integrated results, in which you take the whole emission of the burst and you make your fit and you study. But if you go and then look at, you slice your event, then maybe you can find a pulse which is very short and it's harder. But it gets a little bit washed out if you go and analyze the whole event. But yes, single pulses, especially at the beginning of the burst, tend to be harder. Yes. we saw all of these with Fermi events a lot of times. Maybe I can comment it, if I remember it, I can comment it also in the end, because we saw it also in this very famous boat burst that was the brightest of all time, that I will, if I have the time, I will show it at the end. Okay, so I told you gamma ray bursts can be fit, so their spectrum can be fit by this smoothly joint power law. Basically, so you have alpha, a peak, beta, and that's it, theoretically. So what happened in the 90s, that YGRT and the instruments, well, the various sub-instruments on board inside YGRT, they could measure also energies that were higher. So for some GRBs, they were detected also by YGRT. And so what happened, that obviously YGRT could measure also the spectrum of the burst. And in the, so this is an example of 94, what is it, October 17. So these are different time slices. So this is exactly what I was telling before. So you don't fit the whole emission, but you take your burst, you slice it in different time bins, and you see the spectrum inside each bin, how it evolves to learn something more about the whole emission of your event. So you see from minus 18 to 14 seconds, and then up to 200 seconds. And this is the nu representation. Okay, it's very squeezed, so it's not very easy to see, but this would be the band function somehow. It's not, as I said, it's not easy to see. But if you go down in the sense that you move on in time, you see that there are more data points, the black ones, that are from YGRT at higher energies, and the spectrum is not going down, because with band you should go down, and that's it, end of the story. The spectrum is rising again. Do you know the AGN spectra with the two bumps? Down and up again. This can remind you something about this, just to give you an idea. So there is something, there is a rebrightening. So what is happening is that at longer times, there is a spectral, an extra spectral component that tells you something else is happening inside the burst. And these were just very few cases. I didn't write it here. This was the most famous. All of these events that I show you here, they were basically papers published in Nature. Just to let you know how important is all of this. All of this. Also, this one, this was the so-called Super Bowl burst. Also because I forgot to say something extremely important. Usually, the most important bursts happen in Christmas, New Year's, when you are basically on vacation, all the time. So this one was the Super Bowl. So for the US community, Super Bowl is like, it's always like this. So you know the burst that I will talk about this afternoon, the gravitational wave one, it happened on the 17th of August. I was on the beach. And I was on the beach, and my phone was Franz, obviously, calling me like, you must go to your laptop, you must do something. I was, Franz, I am on the beach, I am at the sea, what can I do? Yes, but there is the burst of the history. Okay, it's always like this. So you are all the day, all the time in shift to see if there is the burst, and nothing happens. And then the day you take your day off, it happens. Okay, this is it. So this was one of this Super Bowl burst. And what you see, so in green is counts seen by BATSI. So it's just a 2 peaks burst, nothing special. In 2 seconds, so it's a very short burst. But look at this. So these are the YGRT photons. They are more or less together, so detected at the same time than BATSI, but then 1, 2, 3, 4, 5, 6. So once that the BATSI is not seeing anything more, YGRT is seeing still photons, high energy photons coming from the source. So this is telling us another story. So there must be something more coming from the burst, not only during this first emission in gamma rays. So this is still gamma rays, but at higher energies. And this is another most famous Nature event by Harley and collaborators of February '94. And in this, so it's a little bit complicated, this plot, but you have let's say the trigger time is here, okay? And you have all of the, let's say, here are the photon energies. Here you have, there is the first, let's say, the main emission of the event. And then usually what happens, also in Fermi, that your satellite goes around the Earth, it orbits the Earth, and so it is offline, so to say, for some time, and then you see again. And what is happening? That after the Earth occultation time, there were still photons coming from the source. And this guy here was, if I wrote it somewhere, did I? No, I didn't write it somewhere. Ah, yes, the 18 GeV. 18 GeV. So this is why it was nature again, obviously. So this was detected 75 minutes, not seconds, after trigger time. Once the Batze light curve was super dead, not dead, like super dead, 75 minutes, 18 GeV. So this was one of the most important arguments for having Fermi hunting for high energy gamma ray bursts. Because of these guys, because we knew it, we knew we should see something at high energies, and we did in the end, but anyway. So let me make a brief, okay, let me say something. I am not the so-called afterglow person, because I study what you just saw. So I basically study what we call the prompt emission, so it is happening in gamma rays. But it is super important to explain what is happening basically to gamma ray bursts at all wavelengths. And this was the breakthrough. This was the breakthrough thanks to this very small, very minor, it also worked for very few years, just 6 years, this satellite, which was called the Beppo SAX, in honor of Giuseppe Occhialini, Beppo in Italian, because it was an Italian-Dutch mission. And so it was operative for not for long. And this was the breakthrough. Having 3 instruments on board, not on the same, obviously, energy range, but not like in Batze going up in energy, going down. You see, it had the X-ray telescopes. Okay, 300 kV, I told you it depends on who you are asking, if it's X-ray or gamma rays, anyway. Then these wide field cameras, really low energy, and then you had the gamma ray burst monitor, okay? And so what was the issue? That you can trigger your instrument, and then you get a position which is of the order, let's say, of the arc minute. It was already very good with these wide field cameras. Then you have your satellite slew to the position, automatically slew to the position. You look with the narrowed field instrument, and you follow up the guy in the X-rays. And this was, I think this was science, not nature, the paper. This one, I think this was science. So basically this is, on what we see on the left, is an X-ray image of this gamma ray burst. So it's a fading X-ray source that it was seen on longer time scales. Again, once the GRB in the gamma rays was long gone, and you saw this on the day, this was seen on the day of the explosion, but I told you, so some minutes, hours even after the burst, and this is just another plot of, let's say, a week afterwards, the 3rd of March, in which you still have a hint of something, but it's definitely fading away. So what is happening? There is another emission that was called traditionally the afterglow emission, that is following the main gamma ray emission at a lower energy range, obviously, and this was the beginning of a completely new era in which the community started to do follow-ups of gamma ray bursts. Because with an X-ray instrument I don't know if you are a little bit, some of you is more instrumental and you have an idea, but with gamma ray instruments, it's really difficult to have small error boxes. While with X-rays or then with optical, then you can have the precision of the arcsecond. And with the precision of the arcsecond, you can really do astrophysics, you can measure distances. And once you measure distances, you know where your source is, and this is exactly what happened. So this was another event. No, this is the same. So it was seen also in the optical band, and you could follow it up from the ground, from optical telescopes. And so this was the first. So there was also an Hubble, because also Hubble is following up, if it can, gamma ray burst. And this was the first host galaxy measurement. So they were able to measure, to see the position of the afterglow in the optical, and they saw that the position of the afterglow is next to a bigger galaxy, and so they attributed the explosion to a region in the, let's say, in the vicinity of the galaxy, which is called the host galaxy, hosting the gamma ray burst. And so this is one way to determine, for example, the distance. So if you can measure the redshift of the host galaxy, we attribute the redshift of the host galaxy also to the gamma ray burst, for obviously through emission line measurements. This I didn't say. This is another event from '97 in May. This was the first detection of a radio afterglow, because then obviously the X optical and also in the radio. These are some radio light curves, and this helped. So you think about all of this. So all of this information was helping theoreticians to build really the model, to understand how it is working. I will talk about this in a minute. And there was also, through radio detection, there was also the first direct GRB redshift measurement, also because you could really study the spectrum of, so you could see emission lines in the afterglow emission itself, not in the host galaxy, but really in the afterglow of the event. And this, for example, was 0.8. So we are cosmological, we are extragalactic, we are really far away. It's not part of the galaxy. Okay, so the observational progress was incredible, because now with the redshift determination, either through host galaxy or through the direct measurement by the optical absorption, so we could really confirm that gamma ray bursts are. And this ended the distance controversy, because there was still someone in the 90s that was convinced that they were galactic, and this ended and also helped for the energetic discussion. Just opening and closing a very short parenthesis. Some gamma ray bursts, and it started in the 90s after, obviously, the afterglow detection and everything, have a shape in their afterglow emission that is extremely similar to the shape of supernovae explosion. So some GRBs are associated with explosion of supernova, but not just a simple supernova. So these are the so-called even hypernovae, so extremely energetic supernovae, usually of the type 1bc. Usually this is the most, how do you say, the most frequent case. Not all GRBs that we saw, but there is a certain number of events, and there is a whole study of gamma ray burst supernova connection. So in fact, this is also how I started when I was a master student with the gamma ray burst studies. I also started with this, studying these few cases that are in the literature. So studying these optical and radio and let's say the light curves of this afterglow, what could be seen is that the afterglow somehow is decaying also at longer time. So you see here, this is days after the burst. So really you can follow up gamma ray burst afterglows for days, or what we will see also this afternoon, even for years. If the source is still shining, you can stay. And if you have time with a satellite or with a telescope or with whatever, you have a good proposal and you can follow up the burst. And so what was seen at the time is that there are these breaks in the light curves that are somehow achromatic, so at all different, you see the different colors, B, V, R, I, and then now it in the optical. And this was attributed to the presence of a jet. This is what I wanted to tell you. So we need to understand a little bit what the model of a gamma ray burst is. So somehow it's a jetted emission. And so this could be a so-called jet break. And I should have a cartoon here just to show you what I mean by jet break. So basically, we must have some explosion that is producing this jetted emission. And you have these breaks once the jet is opening. Why? Because it is encountering other interstellar material. It's opening up. And this is the, so to say, the scheme of what is happening. So it starts with an initial relatively well-beamed radiation cone, and then this is opening, and this is what we see, basically, into a larger cone, and these are the breaks that we follow over longer time scales, as I see. The polarization, I will skip it completely. Okay, just a few words, because I think it's important also, because this is a lecture on gamma ray bursts. So in the 90s, gathering all of this information about the afterglow, basically, but also with the gamma ray information that was already discussed for decades, as I told you, this is the picture that built up over these years. And it's called the fireball model. So this describes a little bit what is happening, basically, so what we think that it is happening, because we really don't know, basically. We don't see a gamma ray burst from near. So these are all theories that we have. But after 20, 30 years, we really hope that now we are, let's say, sure about this. Okay, so basically you have, so it was already predicted before, let's say, the discoveries, because as I said, it was already discussed many times. And the idea is that you have somehow some relativistic ejecta coming out from a central catastrophic event, a central explosion that is here, the so-called central engine, which must be something very compact, so basically a black hole. This is what we are talking about. And it is basically interacting with surrounding medium and decelerating. And so let's say the emission is shifting towards softer energy bands. So basically, the idea is putting together all of what I already discussed. So the idea is that you have some emission of material that is moving relativistically, okay? And the characteristic that came from the Batze gamma ray burst to this conclusion are that the fluence and the durations are basically responsible to this. They are connected to this very fast variability that I was talking about before. Then this is connected also to the high energies that were seen by Ygritte, and also the fact that the spectrum is non-thermal. So the energies, to give you an idea about how high maybe some of you know about the energies of supernovae explosion. Supernovae explosion are around, let's say, 10 to the 43, 44 erg, more or less, the total emitted energy. So if you do this kind of calculation for gamma ray bursts, assuming some fluence, assuming some duration, so this is why you have these formulae that are the formulae that I call the ones to give you a little bit an idea, to know the order of magnitude. So basically, the idea, so the energy budget, the energy reservoir of a gamma ray burst is of the order of 10 more than 10 to the 50 erg, 10 to the 51. The strongest one arrived to 10 to the 53 or 10 to the 54 erg. So extremely, much more energetic than an AGN or a blazar, obviously, because they go down to 49, 48, more or less. So this is the energy budget. And this is the problem, that you don't have an AGN on the time scales. Some of you maybe know what is a time scale of, for example, a flare of an AGN. It takes days, weeks, and this you have to put this energy inside something that sometimes it's lasting 10 milliseconds, and so which is insane somehow. And so the scale of the emission area needs to be extremely small. So the idea is that you need to have something compact that is of the order of the kilometer. So we are talking about super compact objects, basically. And so you have to do some mathematics. I don't want to bother you too much. But in general, you can go, so this FP that you find in the formula is the fraction of photons above the energy threshold of the electron-positron per production. Okay, let's not go too much into the detail. But basically, you can go and calculate the per production optical depth. Okay, so what is the problem? That this value of this 10 to the 13, then, okay, you have to decide the distance, the fluence, the time, whatever. You have a very huge value, so this is too high, okay? It would generate an optically thick fireball, and it would lead to a thermalization. Thermalization, we don't want it, we don't see it, we don't see, so this would be inconsistent. So what is happening? So they should have been attenuated before traveling, but this is not possible. And so how do you solve this? With the relativistic motion. So what is happening inside the jet is basically that everything is moving at the speed of light, almost the speed of light, okay? So there is this plasma that is moving inside the jet, is moving relativistically, and you have to add the Lorentz factor gamma. So this is the trick. You add the factor gamma, and so then you change, basically you have to change the FP by a particular factor. You find another real physical scale which is a little bit different, and if you combine the effects, you reduce the optical depth by a very large factor. And basically, just to give you an idea, and this is what we really calculated, for example, in all of the Fermi events, you can go and make and try to calculate what is the gamma, so to get an idea, so how high could be the Lorentz factor. So we are talking about Lorentz factors that can be 100 or above. So extremely, extremely large Lorentz factors. So basically, the GRBs involve the fastest bulk motion known so far in the universe. Obviously, it's not a pure photon fireball, but it is a little bit baryon polluted, okay? During the expansion, I don't want to go really, I leave you the slides because if you are interested, you can read a little bit more, but I don't want to go too much into the detail. But I wanted to jump to this thing here. So what is happening basically inside? So why do we see all the spikes? What is happening inside the jet? So basically inside the jet we have this relativistically moving plasma, and we model it through different shells. And when the different shells have different speeds inside the jet and they collide, the slowest with the fastest, they produce these so-called internal shocks. And this is all the variability that we see basically in the prompt emission that we measure in the gamma rays, with our gamma ray satellites, so to say. So basically you have this when faster moving shells catch the slower ones. Okay, these are, and you have all of the, now I don't have really the time to go so much into the detail, but you can go and calculate the range scale. I don't know why we astrophysicists like to have things like erg, centimeters. And you know, I also teach to engineering students, and I always teach them everything needs to be meters, and then I myself use centimeters. Okay, I close the parentheses. So this is an idea of again, this is one of the very old 90s sketches. We have also more recent ones, but I like this one. And what is happening with this afterglow? So what is happening once once the shells are interacting with the local medium? So because you have to imagine, you have, I didn't say yet, I will say it in a few, spoiler, okay? So you basically have a very big star, massive star that is collapsing. So you have the jets starting from the inside, from the central, it's called the central engine, from the core, so where the black hole is born, so to say, going out of the material of the star itself, and this is the internal shocks, the prompt emission. And once you arrive completely outside to the local medium, to the interstellar medium, then you have these so-called external shocks that are the one responsible for the afterglow emission over longer time scales. So, and here you have again the centimeter scale of what is happening at the very end, and basically this is getting, so it's producing all of the other. And here you have also another, so this is another, would have been another lecture. This is basically how we do all of the modeling of the afterglow light curves. I don't have the time to go into detail because it's really another world, the afterglow. I will just show you a couple of results by Swift. In general, what I highlight in this slide, you can read it at home, then after on, GRB physics is complex, and it involves very difficult microphysics. So it's plasma physics, it's relativistically, it's complicated. But if you are interested, I think it's also an extremely amazing science. Okay, I gave you also a couple of, of plots more that you can take a look at. Okay, just 2 words about Swift. So basically, Swift took the experience of BeppoSAX, but making it much better, because it was launched in 2005 and it's still up there. It's an amazing mission, really. Multi-wavelength, again, so with the main gamma ray detector, and then it has an X-ray detector and a UV monitor. I think I have all of the, where is it? Here are the 3 instruments on board, so you have this coded mass detector. The only problem with Swift, well, not for me, not for the world, just for Elisabetta, it's this, that the BAT instrument has a low energy. It's not going up in energy. And this is really making me crazy, because you cannot do, let's say, proper prompt emission analysis with Swift-only data. Because you remember where is E peak, the maximum, the distribution. It's around more than 200 keV. So with this instrument, you are only looking half of the story of the gamma ray burst. And this drives me crazy. But the good thing is that we have, for now, this plus Fermi orbiting. So you put together the information about the 2 instruments, and your life is happy again. But in general, this is the problem. Well, it's the problem for me because I like, let's say, the gamma ray part, but the wonderful thing is what is written down here. So the X-ray instrument and the UV instrument, because they provide arc-second precision measurement of the position, and again, also Swift is slewing automatically to follow up gamma ray bursts. So this was the key to the success of Swift, and Swift achievement, basically, Swift study was what I told you before, the X-ray afterglow. We have so many events now. We have thousands of gamma ray bursts over the past 20 years, because Swift celebrated this March with a very nice symposium in Italy, 20 years of mission, and we have so many of these events. You see, this is a light curve of an event with the BAT data, so the gamma ray data, and then you see the evolution of the X-ray light curve, and you see spikes, you see, let's say, a plateau, then again going down. And so basically, you could study what is happening, afterglow physics, basically. It also discovered for the first time afterglows for short GRBs, because with BeppoSAX they were not seen, so it was also seen this. And then also high redshift GRBs. So we have some GRBs that are at redshift 9 or 8, so they are extremely, extremely far events. Okay, for your curiosity, I don't go into the detail, also because I am absolutely not an expert of canonical X-ray light curves, but this is just to give you an idea, and this is a very nice review by Maria Grazia Bernardini, yes, for 2018. So if you are curious, I advise you to read this paper. Okay, this is a collection of long GRBs and a collection of short GRB afterglows. I think we can skip this. But I just want to pinpoint this, because since a couple of years now, we have this very nice tool for the community, which is called AstroColibri. There is our colleague Fabian, exactly, who is one of the responsible for this project. And so this is basically an app. I think you can install it also on your mobile phone, if I'm not mistaken. And you can do it at the beach. Perfect, exactly. So basically it shows you all of the light curves ever seen by XRT. And you can, in different colors, obviously, you can highlight, for example, your GRB of your heart. And in this example, you have this GRB that I wanted to show you at the end, which was the brightest of all times. And you see that a GRB that is bright in gamma, because we know that it is bright in gamma, it's also the brightest by far of all of the X-ray light curves seen by Swift in all of its lifetime. So this was really amazing. The redshift distribution I will skip. Okay, what I can say is that what was also a part of all of this journey about learning how to model the jet physics of a gamma ray burst was to understand what is the central engine. So what is kicking in the jet production. So the idea is that the long gamma ray bursts are basically big stars that are collapsing. So usually they are these Wolf-Rayet, very big 25 solar masses, even bigger solar masses, in which they are basically collapsing on themselves and producing these two jets in the opposite direction, while the short burst should be produced by the merger of two compact objects, like, for example, two neutron stars, so a binary star neutron star system. But we will discuss it a little bit more also in the afternoon with gravitational waves. So this is a little bit the one, I think, of the last, this is not the most recent plot. It's again a little bit old. But in general, you have the idea of the merger scenario producing the black hole and then the jet for the short events, and the so-called hypernova, so the collapsar scenario that is producing the black hole and then. But again, there are a few cases now also recently in the literature that are not really, that are also putting some problems, because sometimes we see short gamma ray bursts that are also connected to a hypernova. So it becomes a little bit difficult. But as I said, if you've seen one GRB, you've seen one GRB. So there are also, I will skip the cosmological use because now we don't have time. So where are we now? So this is a slide of Gabriele Ghisellini of 2010 that I like very much, because when I started to study gamma ray burst, I said, come on, but are we sure about something about gamma ray burst, or is it everything that it could be, it might be? So this is what Gabriele calls the pillars of knowledge. So you say, you are sure that this is, okay, GRBs are cosmological. We believe it is not put into. GRBs have large bulk Lorentz factors. Yes, absolutely. The prompt and afterglow emission phases must be something somehow different from each other. So once it's produced in one place inside the jet, the other one when the jet is colliding. So this is a little bit what you can say. What did I learn today about gamma ray bursts? These three things. And you are good to go. And these were the GRB detection rates before Fermi arrived. And last thing before Fermi, maybe you know, also for AGN, we have the ATEL system. For gamma ray bursts, we have this gamma ray burst coordinate network. And this is actually, this was built, so this, this plot again is from the 90s, because this was built in the 90s. And the idea is, I have two instruments, let's put them somehow automatically in communication without so much human intervention, because this is the problem. If you start to have a human in the loop, everything gets a little bit more slower. So the idea is to have a network, an automatic network of satellites, ground-based facilities, whatever, and everything goes in a single system. Now this is the scheme of the 90s. As I said, now the situation is completely different in the sense that this one has been wonderfully expanded, and now on my mobile phone I have GCNs streaming all the time, and if I am on the beach, I get a GCN that something is happening. But it is wonderful because everything that is happening also, for example, with neutrinos, gravitational waves, and everything is super interconnected, and you can follow up an event at all wavelengths and with all messengers, because if also neutrino and gravitational waves are in the loop, everyone can follow up everything, basically. So this is the instrument of my heart, so Fermi. So the gamma ray burst monitor is the idea of BATSI, so having all of the instruments that are inorganic scintillator detectors, so sodium iodide and bismuth germanate, all around the spacecraft. And you have the per-conversion telescope, the high energy, on top of it. It has a huge field of view and a large energy range. So this is what I was saying before. So basically, GBM is looking at the whole unocculted sky, apart from the Earth, obviously. LAT field of view is a little bit smaller, but this is what I like for, so this was basically the prospect with which we started the mission. So what do you see? Can you detect gamma ray bursts? Well, actually, yes. I mean, the instrument is called gamma ray burst monitor, so it was built for seeing gamma ray bursts, obviously. But you see, we are covering a very big energy range in order to get the whole peak, because you see Swift sometimes is cutting out. And also the BATSI energy range was a little bit more limited, so this is really very wide. Plus, we have the Large Area Telescope, and we can see what is happening with possible, possible extra. Okay, I will skip how it works, and I will skip also this because we already said. Okay, so what, extremely fast, what happened over the past 18 years, because Fermi was launched in 2008, so it's less years than Swift. We did a lot of work. We did a lot of publication. We had many GBM only, LAT only, but actually the collaboration is, let's say, we are all together, so basically we have a GRB group that is common to both collaborations. So these are all papers that were done together with scientists from GBM and from LAT. We have individual catalogs and, let's say, population studies that I will show you a little bit if I have time, because it's almost 12:30. You have all of the data of Fermi is public, you probably all know. So you can do everything that you want. Plus, you have also all the catalog tables and everything. So if you want to see or start to analyzing, you have the tools are online. You can ask me, and you can do your own science even without being in the collaboration. Okay, like BATSE, this is what GBM saw. This is the 10-year, but it's not that different. Black and red are long and short, nothing spectacular. But we have, so I'm not sure about the 4056, because I have to say it was last week, not today. So maybe today it's 4060 GRB, but it's a lot of events. Is it working? Yes. And what I wanted to show you is an analysis that we did for the catalog of the 10 years now that was published in 2020. So this, it's not very, okay, it's again a little bit squeezed, but this is again the bimodal distribution of the duration. So it's less prominent than the one of BATSI because we have many more events. But the nice thing is that if you go and do a very thorough statistical analysis, you find that the joining point, let's say, between the two Gaussians of the two distributions, the short and the long ones, it's more towards something like 6 seconds rather than 2. So this is why I think that the 2 seconds is a little bit outdated, because it's actually the short ones tend to be a little longer than what we believe. Okay, spectral results. You can look at the publication. You can see a lot of. I will skip it because basically we confirm what BATSE saw, roughly. It's a little bit different. Here you have all of the possible comparison with the BATSE catalogs. Also, this one I want to skip. This is the catalog of the bursts we saw with the Large Area Telescope. Obviously, behind you see the high energy sky, and the green dots are the bursts that we publish in the catalog. The catalog was published in 2019, and we had 186. Now, as of today, we have 200 and more or less, 270 events. This long and short was of the catalog. So let me skip this. So let's spend 2 minutes on this slide, because this I like very much. So these two guys happened at the beginning of the mission. I don't know why the best events, they happened right away, because this happened in September. We launched in June. And this happened in May, so even less than 1 year after launch. So if you see them like this, so these are light curves. If you go from the top to the bottom, you go from the low energies, so NAIs, so low energy, up to 5 MeV, so sorry, 250 kV, then 5 MeV, 10 MeV, and then here you have the large area telescope data, so the high energy data. They don't look that different, more or less. You have some, you see some emission at the very beginning, and then you have many photons coming all the way after seconds and seconds. The nice thing is, but it's not cutted. The nice thing is that this one is a long GRB, because this goes up to 100, while this goes to 5. So one was a long and the other was a short. And both these guys, okay, I have all of the difference here. Okay, obviously they were, again, Science, Nature, Publication, blah, blah, because they had, so this was the first one that had a photon up here that was a 30 GeV photon, so it was much higher than the 18 GeV photons of Egret, so this one was the highest at that moment that was seen by any instrument. And this one was the first short one seen at high energies in general, so this was an amazing event. Another amazing event was the so-called monster burst in 2013, which was so bright that it saturated the gamma ray burst monitor. So you see here it's completely like it's cut, because when you have too many counts, your instrument doesn't work anymore, basically. And so you cannot do so much science in the end. And so the whole science that we did on this event was on the precursor peak, this peak here, that we dedicated an extra paper only for this guy. And it had one of the longest afterglow ever, let's say in gamma rays, this guy here. And it was a wonderful target for Cherenkov telescopes. However, there was full moon. This is a problem. Yes, this is a problem with Cherenkov telescopes. And so there was only an upper limit by the Veritas Cherenkov telescope after 1.5 or 2 days from the emission, but it would have been detectable more or less here around 10 to the 4 to 10 to the 5 seconds. And this guy had also the highest energy photon, the 95 GeV photon. Okay, I will completely skip to the last part, otherwise. So here you have all of the properties at high energies, okay, that I cannot talk about because it's 22, okay. Let me move. Okay, so let me just say this. Okay, what is happening at very high energy? Because I promised you I would tell you something about the very high energies, let me say. So nothing was seen until 2019. The instruments were all there. Magic, Hess, Veritas, they followed up a lot of bursts, nothing. These were the ideas of what I told you before, so there has to be another emission. There were the hints. There are the hints in Fermi that I now went away fast, but there are, so if you go back and you look at the slides, you find them. So what was the problem? There were only some upper limits. This is the monster, no, where is this is the monster burst. Only upper limits until 2019, and then all in once, 2 bursts. It's always like this. You wait 30 years, and then you have 2 bursts at the same time, one by Hess, one by Magic, and this was a special issue by Nature that took both the papers of both collaboration in the same issue describing this, but they were extremely different, because one was seen deep in the afterglow, And the other was seen in the prompt. So let's start from the, let's say, from the afterglow one. And one might ask, but why was it seen in the afterglow? Because this guy exploded at midday, also for Namibia. So during the day, you cannot operate, obviously, Cherenkov telescope. So the delay of this observation is 10 hours after trigger, because it was at the beginning of the night. This is just an example plot after how many days? 27, I don't remember now, I didn't write it here. 18. Nearby, the very high energy GRBs are basically seen nearby, because otherwise the emission, the very high energy emission is cut out. This is just an example of a multi-wavelength light curve. In this case, there is just 1 point of S, which is the red point, but you can discuss about the spectrum. Okay, but I want to show you the other one. So this is the amazing one. So this is the one seen by magic. And this was seen in the prompt. So well, right after, so to say, but almost with no delay. Okay, this is not working. Okay, there is some audio, but it's just a funny audio. So basically, this is how fast the photons arrived in the magic detector. The magic detector, you know, there are mirrors and the camera. It's completely different, but you will learn it this afternoon, I think. But this is amazing, because usually what you use in very high energy is the Crab Nebula as your standard candle, let's say, to make your calibrations. And this is how fast the signal, because you cannot believe it. I mean, it took 30 years to get this. So everyone was completely crazy. As far as I know, in the control room of magic, people were getting completely crazy, like completely crazy, because they could not believe that there was such a okay, this is just the gamma ray thing, but here you have the magic data. The green ones of the light curve here are the magic data together with all the others. So this is the beauty of doing multi-wavelength analysis, that you have everything from gamma rays, then to the X-rays, you have radio, you have optical, you have the whole picture, and this is really, really amazing of this event here. And you can study the spectrum of this guy, and you see here the shape. And so the idea is that this extra component that you see with magic is basically generated by a synchrotron self-compton. So the synchrotron photons are compton upscattered by the same electron that are accelerated in the shocks. So this is the, let's say, the picture that we have right now to understand this second emission that is seen by, well, not so many events, because we just have 6. But it's less than nothing, okay? It's not 4,000, but it's okay. The blue and the pink are Hess and the magic bursts. The last published, it was published at the end of 24, is this guy here, 2012-16C, which has a 6 sigma detection in magic, 57 seconds post-trigger, so extremely fast repointing also for, you have to be also obviously a little bit lucky with Cherenkov telescopes, but with CTAO it will be different. I don't know who will talk about CTAO, but you will listen about it, and it was amazing because it was relatively far away. 1.1 is already pretty far away. I don't want to go into the detail, I promise I am done in 3 minutes. Okay, let me just say this. If you are curious, this is a wonderful, really a wonderful review. I want to advertise this review by Davide Miceli and Lara Nava, because it talks a little bit more about the afterglow physics, focusing on the very high energy event. It's based on few events, you see, but it's really comprehensive, very nice, a bit theoretical for you, for those of you who are more theoretical, but it's really, really a nice, I really suggest it for a reading if you're curious. I want to finish with this guy, the boat. I don't know if you ever heard about it, but in gamma ray burst, let's say, community, this is the guy. So boat means the brightest of all time. So it happened in October 22. And I was on shift. I was very proud. It was a Sunday evening, but it was worth it. It was absolutely worth it. So this is just a burst popping up. So this is LAT data when you image it. it's boring. I mean, if you do it with X-rays, with optical, you get all these colors. While in gamma rays, you just have this. And you say, and this is the strongest of all, so you can imagine the others. But anyway, okay, so it was a disaster because the GCNs went on for 3 days full, like every hour a GCN was coming. Everyone saw this burst, swift. There were X-ray rings. It was unbelievable. It was really amazing. With FLAT, we saw the highest energy photon ever from a gamma ray burst. It was the 99 GeV, but actually we found then later on also a 400 GeV photon, so this was incredible. And this was seen also by LASO at the TeV. So why, you could ask, but the Cherenkov telescopes? There was again full moon. Obviously, so it's the second time. After 130427, that was the monster, there was again full moon. Okay, I don't know what to say because this is life, but there was also no neutrino detection, just to tell you, because obviously it was followed up a lot. This is the LASO detection. There is a very nice paper by the LASO collaboration, and you know, I showed you a lot of light curves today, with a lot of photons, and the red ones were GeV photons of Fermi, okay, or of Ygritte. This is TeV photons. So for me, it's amazing. I mean, even when I look at this picture, I still cannot believe it somehow. But anyway, I don't want absolutely. So obviously, we had problems with saturation because obviously it was completely saturated, both GBM, LAT. It was a nightmare. It took us a lot of time because we published this year all of our analysis. And just to tell you what we did is we analyzed just the very first second of the burst, and this goes into the direction of the question of before. The very first second was so hard that it had an energy of about 13 MeV, the peak energy of just this first second. And then there was this whole emission that had the saturation, and there were all of the studies that I will completely skip. You can take a look afterwards. I won't go into the detail now. Absolutely, if it goes on. Okay, it's basically, if you don't believe it, because we call it the burst, the brightest of the boat. So there was a paper which we published together with GBM and with a lot of people of the transient gamma ray community, basically, that studied 55 years of data, so all of the data that were for gamma ray bursts that were available, and we basically saw that apart from the isotropic luminosity, in which it was basically the third highest measurement, it was the highest of all. So it is the boat. And I want just to mention a paper that came out last month, because I told you that the Cherenkov telescope were unfortunately in full moon, but with the newest technologies that, for example, the LST has with the silicon photomultipliers and all of the other technologies, we have the possibility to see the burst also with partial full moon. And so they tried lots of different analyses to recover the data, and in fact, they recovered the 4 sigma. 4 sigma, okay, you know that in physics, if it's not 5 sigma, but nevertheless, it's 4. And so there are some upper limits that are extremely important, because already with these 4 upper limits here, you can already disentangle between different theoretical models, and you can rule out the models that are on top. So even if you have just an upper limit, it can be extremely, extremely valuable. Okay, this is just a nice picture that shows you some of the bursts that I told. The 17 we will see this afternoon. This is 090510. This was another one that was not so interesting, okay? Let's skip it. This was one of my favorite ones because it was when it was my birthday, obviously. And I was on shift, obviously. Then this is the magic one, 1904-14C. The monster burst, which is, again, you see the count rate is always happening. And then you have the monster. And so you have them all in scale, basically. So the monster was really, well, not the monster, the boat was really the highest. And here you have all of the different. OK, I'm really done. That's it. Sorry for.
Thank you, Elisabetta. I think that was a lot of fun. I want to jump in with one question. Can you comment something about the electron-positron line in the boat?
Ah, yes. I don't remember if I have the slide. I hope. I don't remember if I put the. I should have. No, I don't have the plot. I'm sorry. I had it in the talk of the conference. So what happened here, I don't have the plot in the slides, sorry. So what happened here, now this is the light curve still, I don't have the spectrum. No, I don't have the spectrum. So what was happening, I can just explain it. You can imagine it. So basically, the main emission of the burst came around, where is it? Okay, here you see it. So between 230 and 300 keV, and then so it was very bright until 600 seconds after the burst. And what is happening is that inside so when you study the spectrum of the burst, we were trying within the Fermi GBM and Fermi-LAT collaboration to see the spectral shape and fitting it with the usual band function. Okay. And it was very bad. It was very bad. OK, how do we fit it? There was some kind of a strange bump or something. And then, as it happens a lot of time in science, a competitor group, which is not inside the collaboration, had the idea to add to the spectral analysis, to the usual band function, an extra Gaussian line. And the Gaussian line, that is, I'm really sorry I don't have the image here, was fitting very, very well the data, not only at 250, but I think it was at least in 4 different time slices. And it was interpreted, because it's really difficult to interpret, as this electron-positron blue-shifted line that was not seen. So there are a lot of already theoretical papers that were looking for this kind of line in other bursts. So far, we did not find it, also because this was really the brightest one. So maybe it's also because I have to say that the GBM team at the beginning, so we had several calls in which we were thinking about instrumental effects, that it was somehow due to the instrument. But so I was involved, when I was a PhD student, I was involved in the calibration of GBM, and we have nothing that could produce such a strong line at 10 MeV. Because all of the other lines that we know, the phosphorescence, apart from the time scales that are much shorter, because they die much more quicker, but they are not at 10 MeV. So we could not explain it. We could not explain it with an instrumental effect. Then I don't know if it is really, because there are some in the community that really don't believe it somehow. I know, because there are some papers that are really strong against it, but right now it's the interpretation that we have. But it's the only one.
So what's the mean? Plus and minus is annihilation?
Yes, yes, right. Yes.
OK. More questions?
I think everyone
Claudio?
is starving. I'm sorry.
Yeah. Well, you said, I kind of got worried with this 10 to the 51 or 54
yes,
ergs,
yes.
Yeah? Because the sun produces like 10 to the 26 watts.
Okay. Ah, watts, OK.
OK? Wait.
Okay.
During 10 billion years,
yes,
so you convert to seconds, convert to ergs, whatever, and it gives me 10 to the 49 ergs.
Possible, yes. Yeah, gamma ray bursts are stronger than the sun. They emit more energy than the whole sun in their life. Yes, it's correct.
OK.
It's absolutely correct. You did the right calculation.
I hope we don't get anything like that close by.
No. You know, there were theories that were thinking that dinosaurs were extincted by a gamma ray burst explosion nearby. but no, obviously. But so we don't have any stellar system in our galaxy that is in this shape that could produce a gamma ray burst, because you really, so the fact that they are cosmological, it means that they are primordial stars, basically, huge stars that are producing this. So they are not, we don't have such kind of stars in our galaxy, basically.
But for example, for the boat, I remember that there was a paper that analyzed the effect in the upper atmosphere of the gamma ray flux.
Absolutely.
So it affected the atmosphere of Earth.
Yeah, but actually, so the boat was seen by, I think, every satellite that was in the direction. It was seen by the probes around Mars, and I'm not sure around Venus, but around Mars for sure, because it was in the direction of the Earth, and so it was measured. So it basically every instrument had some kind of effect. All of the satellites. So there was and this is why there was this incredibly huge follow-up. Yes.
It could still be dangerous. Okay, anyone else? Yes.
Hi. Thank you for the talk. It was really fun. So I was thinking, is there a reason for that we see increasing energy? Because I thought first, okay, we are getting better instruments, but previous gamma ray bursts don't saturate the instruments, so why are they increasing in energy?
Okay, so the point is that the very, very, very high energies, like the boat ones, are extremely rare ones. So we calculated also this. And the boat is like, I don't remember now the number, but it's like less than 1 per century. So it's extremely rare. So this is question. So answer number one. So basically, there are just very few events. The fact about why we did detect them all of a sudden and nothing before, it's a mixture of technological advancements, in the sense that between 2000 and, now I don't remember exactly the years, but there were major upgrades in the mirrors and in the, maybe also in the cameras, I don't remember. For sure in HESS, because in HESS there was also the, but also in MAGIC. Both, exactly. So, and also the software, so there were lots of advancements. And then, I don't know, luck, I think. I know that there was a burst in, now I don't remember the year, in 2000 and, I think I was doing my PhD, maybe it was 2008, and I know there was a guy, Galanti, I don't remember if you ever know, who was in the control room of MAGIC once a GRB happened and he did not push a button or something like this. Yes. It was so famous, this fact, that I also that was sitting somewhere else, not in the MAGIC collaboration, at some point even I knew it. So I don't know if it is true because it's so many years ago that I'm not really sure. But there are, so I didn't talk a lot, but there are a few cases of upper limits also in the past. So basically, we knew that there was something. It was simply that we were not probably good enough.
But you know, I would add something else. I don't know if you agree, but I mean, in science, to make a claim, of course, you need all the studies and the data, but you need a bit of courage. And I say that because one of the bursts that has put up now from 2016 is this 3 sigma, yes. But they advertise. But the one from HESS, I mean, MAGIC observed the first detection of a burst in 2019. The one that HESS published in the same issue of Nature was from 2018.
Yes, was it? Yes.
So they didn't have the courage.
Yes, I know. And I am part of the HESS collaboration, if you want, I tell you the whole story. Because I was sitting in the calls, and it was actually in the hands of a PhD student who was analyzing the data like 1 time, 2 times, 3 times, and he was like, there is something, yes. But you know, before you have to convince the whole collaboration, then when MAGIC saw the burst, they said, okay, but also that our was, and so, okay, I understand.
Hi, thanks for the talk. This is a very quick question. Could you please go back to the slide 86?
80, Mom, I have too many slides.
Okay, great, thanks. I see synchrotron, self-synchrotron, but what's the... So the blue line is just the summation of the both curves, right?
The colors, now I don't remember anymore. Let me look at it like this. So I think the blue was the total. I can look at it up if you want in the lunch break. This butterfly effect there is it's basically the error box of Fermi-Lat data that have a very large, have some uncertainty. So this red spot there, I don't know if this was your question, is the Fermi-Lat uncertainty. And the black lines below are the single models.
Okay, thank you.
Sure.
Okay, so I guess
Yeah,
we are done because
we
you have to have lunch. You have to have lunch to be able to continue the lecture in the afternoon. Okay,
Okay.
thank you very much.
Thank you.